In polar coordinates, where the velocity vector is er vr plus e theta v theta, a flow is described by vr equals m over 2 pi r, v theta equals 0. 1. Sketch the flow. 2. Show that div v equals 0. And 3. Find an expression for the acceleration of a fluid blob as it passes a point in the flow. So let's start by defining an origin, that point there, and we can see from the flow Vr is equal to something v theta is 0. That means that everything is moving in a radial direction away from that point. So there's no motion in the theta direction, everything is moving away. What's more, near the origin it's moving pretty quickly, and further away from the origin it's moving slower. In fact, if you want to look at it a bit more detail, you'll see that 2 pi r times Vr is equal to m, which is a constant, and so that's telling you essentially that the volumetric flow rate at circles of radius r is a constant. Next we're asked to show that div v is equal to 0. We have to be careful here because we're using polar coordinates rather than Cartesian coordinates. So let's just write down the definition of the del operator. So the del is defined as er d by dr plus e theta over r d by d theta. And if you ever get confused about where to put the 1 over r and this sort of thing, just note that the two sides have to be, if you like, dimensionally consistent. So if r had dimensions of meters, we'd have to have a 1 over r with the e theta. Now we have to be careful of the things that go on the right of the d by d theta expression, and that's because d by d theta of the unit vector is not equal to 0. D by d theta of Vr is equal to e theta, and d by d theta of e theta is equal to minus er. However, we don't have to be quite so careful with what goes to the right of the d by dr, because d by dr of the unit vectors er or e theta is both equal to 0. So we need to expand out the expression for div v. So let's simply substitute in this expression for the del operator. It's er d by dr plus e theta over r d by d theta, and it acts on the velocity vector v, which we're told in this case is just er times vr, which is m over 2 pi r. Normally there'd be an e theta component, but that is equal to 0 in this case. Now there should be a scalar product in there. Let's do the er term. We've got er. Now this d by dr can hop the other side of the scalar product because the scalar product is only telling us how to relate this vector to this vector. So the scalar product goes in there, and the d by dr can also hop the other side of the vector here, simply because d by dr of er is equal to 0. Er does not depend on r. So then we get d by dr of m over 2 pi r, and that's the end of the first expression. Now the next one is the plus e theta over r. Now the d by d theta here again can hop the other side of the scalar product, because the scalar product just tells us how to relate e theta with whatever vector we end up with on the other side. So the dot goes there, d by d theta of er m over 2 pi r. Now the first expression is easy. Er dotted with er is just equal to 1, so this becomes d by dr of m over 2 pi r, which is minus m over 2 pi r squared. The second expression needs a lot more care, so we'll spend some more time on it. We've got e theta still over r, dotted with whatever comes out of this bracket here. Now m over 2 pi r isn't a function of theta, so that can come out. So we've got an m over 2 pi r, and here we've got a d by d theta of er, and if we look at the top, d by d theta of er is equal to e theta. So we've got an e theta here. So we're going to get a minus m over 2 pi r squared from the first term, plus e theta dotted with e theta is 1. This is just m over 2 pi r squared, therefore add the two together and we get 0. So we have confirmed that div v is equal to 0. In other words, if it's an incompressible flow, it satisfies conservation of mass. Now in the next part we have to find an expression for the acceleration of a fluid blob as it passes a point in the flow. So let's take this point here and imagine we've got this sort of blob of fluid floating past. What we're after is the acceleration of that blob. So that's obviously equal to d by dt, ordinary derivative of the velocity of the blob. Now remember, that's the velocity being carried by the blob itself. What we have is an expression for the velocity field, v, x and y, but we know that the material derivative of the velocity field, x and y, or r and theta, whatever the coordinates are, at the blob's position will be the same thing. So in this case then we have d by dt of the velocity, and I'm going to get this right this time, it's r comma theta, because we're expressing it in polar coordinates. Now this is expressed, or the definition of the material derivative is curly d by curly dt plus v dotted with grad of whatever's on the outside, in this case v, and let's put the v inside the brackets. We've got a dv by dt plus v dotted with grad. Altogether that makes a scalar operator acting on the velocity v. Now the first thing to notice is that we have a steady flow, so there's no change in time. dv by dt is equal to 0, and all we have left is this expression on the right. So let's expand out first of all the v dot grad. The v is er vr. There is also the e theta v theta term, but as we know already that goes to 0. So that's the v dotted with grad, which in this case is er d by dr plus e theta over r d by d theta. Now we don't actually have to be quite so careful this time, because all the operators are on the right, until we actually make it operate on v here. So that's, if we just look at this first expression here, which is the v dot grad, what we have is an er dotted with er vr d by dr. This term's equal to 0, so afterwards we have plus er dotted with e theta. Well, we know that's going to be 0, so there's no other term there, and all that will be adding on, acting on v. And let's put in our expression for v in a moment. er dotted with er gives you 1, so what we have is vr d by dr of v, and v is just equal to er vr. Now we know that there's no variation in the r direction of the unit vector, so that can come out, er to the outside, and then we get vr d by dr of vr. Substitute in our expression for vr, we're going to get m over 2 pi r d by dr of m over 2 pi r, and scrolling down, that's equal to er m over 2 pi r times minus m over 2 pi r squared, which is all going to work out as er m squared over 4 pi squared r cubed, with a minus sign at the front. So what does this tell us about the flow? Well, because this is rather a simple flow, it's all rather obvious, but if we have the flow, it's arriving at the point in the middle, it's then moving out, and to start off with, well, we know it moves quite quickly, but we also know it's accelerating when r is small. When this term here is, when r is small, it's accelerating really quite quickly towards the centre. Well, rather it's decelerating as it moves in that direction quite quickly. And then as it moves out, the acceleration towards the centre gets lower and lower as its velocity decreases. So that's what the flow is. It's actually a source term. And it's worth noting that, sure enough, the divergence of the velocity is equal to 0 everywhere, except, and this is important, at the origin. Div v is not equal to 0 at the origin,